Hi, with this video we want to finish Chapter 3 of Young and Freedman's University Physics, or whatever physics textbook you're using. There's a good chance that somewhere in there will be a section on relative velocity. Relative velocity. What is that all about? Well, asking how fast something is moving doesn't actually have a simple answer. It may seem like it's easy enough to ask how fast something is moving, but really we don't quite know how to answer that question unless we know what frame of reference you're talking about. So for example, if somebody's walking on a train, do you want to know the velocity of the person in relation to the train? Or do you want to know the velocity of the person in relation to the ground? Or maybe you want to know the velocity of the person in relation to the sun. Unless we have what's called a frame of reference, we simply don't have enough information to know how to answer the question, how fast something is moving. So a frame of reference is basically a coordinate system, x, y, z, plus a time scale. And the reason why the time scale isn't so important when you're dealing with normal speeds for people like me, or velocities for people like me, or even trains or even planes. In Newtonian physics, that is the physics most given its impetus by Isaac Newton in the 1600s, up until the 20th century, we assumed that time was uniform between various frames of reference. Unfortunately, Einstein pretty much kiboshed all that, at least when we're talking about things moving close to the speed of light. But we're not there yet. That's, I think, Chapter 37 of Young and Freedman's book. So for the moment, we'll assume that time is the same whether you're on a train or whether you're sitting on a park bench by the train. So here's the kind of situation, and really this is common sense. Don't let physics spook you. Some of it's not that hard. So for example, if you're on a train and you're walking forward at 2 miles per hour, and let's say the train is going relatively slow, let's say the train is going 10 miles per hour in relation to me, that's me there sitting on a park bench watching trains as I do, and so how are you going to figure out how fast, let's say it's Joe is on the train walking. Well, in relation to the train, Joe is walking at 2 miles per hour. In relation to me, however, Joe is walking his 2 miles per hour plus the 10 miles per hour of the train in relation to me. And so in relation to me, this is really hard, is 10 plus 2, or 12 miles per hour. So Joe is going to be walking 12 miles per hour in relation to me sitting on the park bench, even though as far as he's concerned, he's walking at 2 miles per hour. You see what I mean by relative velocity. So to figure out relative distances between one frame of reference and another, again, when you're talking about normal speeds, we're not talking about relativity here, forget Einstein, but let's say we have one frame of reference A that's kind of like me sitting on the earth in the park bench, and another frame of reference B, so for example, that was the train in the previous. If we have a point on B, that's what P/B here means, a point on the B frame of reference. And we're going to call this an X frame or X frame. We're just going to bracket out other dimensions and just look at the X component. So if you have if you have Joe located at a certain point on B, X, and then if we could locate that train or the frame of reference B in relation to frame of reference A, so let's say that point of reference B begins at a certain point X, B on A. So by that B/A, I mean what is the difference between frame of reference B and frame of reference A. Then, if I want to locate Joe in relation to the ground, all I do is I take Joe in relation to B, and then I take B as it is located in relation to A, and I add those two X's together, and I get X, Joe's position, P in relation to A. Very simple. I've just taken where Joe is on B and added it to where B is on A, and ta-da, I get Joe's position, P in relation to A. Okay, if that doesn't click, it's not hard. I just haven't explained it well enough. It's just very simple math here. Same thing works for velocities. If I know the velocity of a point on B, so Joe was moving 2 miles per hour, and then if I know the velocity of the B frame of reference in relation to the A frame of reference, so in the example it was the train in relation to the ground, then all I have to do is add the velocities. So if I want to know the velocity of Joe in relation to A, all I do is I take the velocity of Joe in relation to B and add that to the velocity of B frame of reference in relation to A frame of reference. Again, hopefully this is not too hard. Of course, we can't leave a section like this without moving, we just have to jump the shark at some point. So if we treat the equation as a vector, then we can talk about not just one dimension, but we can begin to talk about 2 and 3 dimensions. So by simply putting a bold V, darkening it, and putting that vector line over the top, we have now basically taken the same thing we've been talking about, and we've applied it in relation to 3 dimensions. So this is a robust V. It is a 3-dimensional V. So the vector resultant of P in relation to A is going to be the vector P in relation to B plus the vector frame of reference B in relation to frame of reference A. This is called the Galilean transformation, and it goes back prior to Newton. I think it goes back all the way to Galileo. I think it's not called the Galilean transformation because it came from Galilee or from Jesus, although we could speculate whether Jesus knew this as being God, but certainly he does now. While he was on earth, had he accessed his full omniscience? And you thought this was a physics video. Never mind. Galilean means Galileo, who lived in the 1500s and the turn of the century to 1600. So basically he's the one that came up with this transformation to get from one frame of reference to another frame of reference. So basically what we do is we take the vector P in relation to the B frame of reference, square it, and add it to the vector B frame of reference in relation to A frame of reference, square it, take the square root of all that, and we will have the magnitude of the velocity point in relation to A. This is Pythagorean theorem stuff. The example that Young and Freedman give in the book is of someone who is walking so they're on the train. So the train is moving, but they, instead of moving forward, they decide to walk perpendicular to the path of the train. So we have a nice little vector. We have a vector of the velocity in the direction of the train and the velocity in the relation, in this case, this person has 0 velocity in relation to the train going forward. But they have the velocity of the train in relation to the ground, going that direction. And then on the train, they have this direction of velocity, since they're walking from one side of the train to the other. And so we have a nice little vector equation here. The hypotenuse is going to tell me what their velocity is in relation to the ground. We can do this in 3 dimensions to locate the velocity of one person on one frame of reference in relation to another frame of reference. We can also use trigonometry to figure out the angle at which this person is moving in relation to the ground. I mean, we know on the train they're just moving at a 90 degree angle to the train. But in relation to the ground, since the train is moving, there's going to be an angle that's diagonal. And so we basically use the tangent of that angle. It's going to be the velocity of the point in relation to B frame of reference divided by the velocity of the B frame of reference in relation to the A frame of reference, and that's going to give us the tangent of that angle. If we get the arctangent of V over V, that's going to tell us what the measurement of the angle is. Oh, happy days. Another example he gives is of a plane that's being blown by crosswinds. And so one of the problems is, or one of the examples is, what direction does the plane need to fly into in order for the plane to fly straight without being blown off course? Believe it or not, that's practical. Physics is practical. So this has been Relative Velocities, the last section of Chapter 3 of Young and Freedman's University Physics.